So in last lecture we have started with the optics. So once again we will recap for the 5 minutes, and then after that we will reach to the next topic. Okay, so I will just share my screen. Yes, is the screen visible to everyone?
Yes, sir.
Okay, fine. Okay, so once again we'll just revise quickly, and then we'll move to the today's topic. So we have started with the unit number 2, that is optics. So optics basically means what? So that we are given answer to this optics. The optics is basically a physics of light. Okay, it is a physics of light, and under which we can be able to study the different layers of understanding or describing the light. As you know, the light which is in a different forms, it can be in a particle, it can be in a wave form. So all these types of nature of light, so that also we can be able to study, and different colorizations. So all these things that we can able to study under the optics. Okay, so therefore optics, which is called as physics of light. Okay, so then after this we have discussed about the electromagnetic spectrum. So electromagnetic spectrum, everyone should know what could be the range of this. Okay, and under this we have focused on the visible light spectrum. So what could be the visible light range? So we have seen it is between 400 nanometer to 700 nanometer. Okay, so this is the range. The 400 nanometer is the violet color, and 700 is the red color. So in between there are the different colors. You can be able to see the diagram here, the picture that we have mentioned here. So here the different colors, the 400, that is 440 exactly, and then it reaches to the 700. So that much is the range that we can be able to see with the naked eye. Okay, and if you cross this 400, so that will be your ultraviolet. If you cross the 700, it will be a infrared. Okay, so if your wavelength is below the 400 nanometer, it will be ultraviolet, and if it is above the 700, it will be infrared. So infrared or ultraviolet, that is not been visible to the human eye. Okay, so only the visible spectrum, that is between 400 to 700 nanometer. Okay, so if you want to say in an Armstrong unit, so it will be 4,000 to 7,000 Armstrong unit. Okay, so this is what the visible light in case in the electromagnetic spectrum. Then we have discussed about the interference. So to know about the interference, basically the main condition is to understand the superposition. So superposition is mandatory condition, is that minimum we require the two light waves. Okay, so here we have considered the two light waves of, as you can see, the different colors we are means these light waves are represented by different colors. So one is of purple color, another is of blue color. So both these waves, first two diagram that indicate, that is A and B, that indicate these two waves are in phase. In phase means you can see the starting point of the first wave and the second wave. So both are starting from the same point. Okay, so they are in phase. Okay, so there is no phase difference which is included in these two waves. Okay, so once these two waves they intersect each other, so they can produce the point of maximum, that is amplitude become maximum. So that easily we can be able to see with the help of this diagram, that is A and B. Okay, so we can say whenever there is an amplitude maximum, so we can directly say that it satisfies the condition of constructive interference. Okay, then if you move to the diagram number C, so in this we can see the purple color wave and the blue color. So the both are in a out of phase, means there is a phase difference which is been introduced. Although they start from the same point, but it is out of phase. Okay, it is not in the same manner. Okay, so there is a phase difference which is introduced, and that phase difference is 180 degree. So 180 degree phase difference, that correspond to the wavelength of half, that is lambda by 2. So there is a phase difference and the part difference of lambda by 2 which is introduced between these two waves. So therefore their intersection, that gives you the minimum amplitude. So there is no amplitude which has been generated over here if there is a phase difference of 180 degree. So directly it will satisfy the condition of destructive interference. Okay, so this is how we can be able to get the superposition of the two light waves, whether they are in phase or they are in a out of phase. Okay, so what is their resultant, that also we have seen. So the resultant of the two light waves, that is the superposition principle. Okay, so how it will move to the interference? So for that we need to satisfy some condition. So that conditions are the sources must be coherent. Okay, so this is a mandatory condition to get the interference. The two light sources, they should be coherent. So coherent means they should have the same amplitude, they should have the same or has a constant phase relationship, means either it can be zero or it can be a constant phase. Okay, then and only we can say that the two light waves are in a coherent manner. Okay, so it is the mandatory condition for the for satisfying the interference. Okay, then second mandatory condition is the waves should be monochromatic. The light waves should be monochromatic. So monochromatic means what? The wavelength of that particular light source, it should have a same wavelength, or it should have only single wavelength. Okay, so monochromatic means single color, and single color possess a single wavelength. Okay, so it should have a single color and single wavelength. And then third one, just now we mentioned, they should satisfy the principle of superposition. And last and most important is the waves, they have the same polarizing state. So polarization state is very important to get the interference, because the polarization is the only concept through which we can be able to get the state of vibration of the particles. The particles are vibrating in which state, whether it is in a linear state, or it is a circular, or it is in an elliptical. So what exactly the state of vibration of the particle, so that we can be able to identify with the help of polarization. So if we can be able to satisfy all these four conditions, then the pattern that appears to be called as the interference pattern. Okay, so please try to remember the mandatory conditions for getting the interference pattern. Key, the sources must be coherent, they should be monochromatic, they should superpose, and they satisfy the principle of superposition, and then they should have a same polarizing state. So these four conditions you have to keep in your mind. Okay, it should be on your fingertips also. Then other than this, there is a means, if we satisfy these four conditions, so waves start intersecting each other, and after intersecting they can be able to satisfy the condition of constructive and destructive. Okay, so you can see here from the diagram already we are discussed, but what type of pattern it will produce if we can able to introduce, so that is mentioned over here. Key, in the first diagram, these are the two progressive waves. So once these two progressive waves, they intersect with each other, you can see there are the two colors, one is blue and the another is the green color. So they intersect in phase. Okay, so in phase means there is no phase shift. You can see here, when the phase shift is zero, so wave add constructively. So simple answer, if there is no phase shift, so they add constructively, so their addition you can be able to see with the red color wave. So the red color which has the amplitude greater as compared to the previous waves. Okay, so this indicate there is a constructive interference, and you can be able to get the point of maximum intensity, that is brightness. Okay, then in second diagram, we can see the blue color and the green color waves, they intersect, but in a phase difference of 180 degree. So 180 means there is a phase shift of pi, so therefore the waves add destructively. So there is addition, but that destructive. So you can see with the red color, so it has a very less amplitude. Okay, so amplitude that almost becomes zero if they intersect destructively with the phase shift of pi radian. Okay, so this is what we can be able to say, ki in this case we can be able to get the complete darkness. Okay, so in first case is a complete brightness because of the constructive, and here in second case is the complete darkness because of the destructive. Okay, so these are in sometimes the constructive, destructive, these are called as the intensity maxima or minima, then a condition of brightness or darkness. So all these words are same. Please try to remember, if any question is been asked, like you have to derive the condition for brightness or darkness, or write down the condition for bright or dark, so it means it has been asked like constructive and destructive. Okay, so please try to understand these things. Then we have moved to the methods of interference. So what are the different methods, so that we can be able to produce the coherent sources, because we have to study the interference, And to study the interference, the two sources must be coherent. That is a mandatory condition. So how we can able to get the two sources? Okay, so they should have the same amplitude, same frequency, same wavelength. So how we can able to get this? So for that there are the experimentation which has been done. So one experiment which has been performed by the young scientist. So Young's experiment, so that gives you the division of wavefront. So you are divided a single wavefront in a two different wavefronts, that is S1 and S2. So that two that become a source of secondary. Okay. So two sources which has been generated from a single source, that is S. So that is the condition of division of wavefront. Means a single wavefront is divided into the two. So similar manner here, second method that we have studied is the division of amplitude. So to study this division of amplitude, we have used a thin film. Okay. Now, basically, this division of amplitude that happens only in a thin film. Okay. So what is thin film? That also we have discussed here. So what is thin film? So I just repeat that definition of the thin film. So particular film, a thin film is a film whose thickness is about or of the order of one wavelength of visible light. Okay. So particular film whose thickness is about or of the order of one wavelength of visible light, then and only that film is considered as thin film. Okay. So thin film, it means the wavelength, the thickness of that particular film is of the order of one wavelength of visible light. So one wavelength of visible light, it means it should be of the order of 5500 angstrom unit, or if you talk in terms of the nanometer, so it will be 550 nanometer. Okay, so that much is the thickness that required to get the thin film. Okay, so thin film basically depends upon the thickness, and that should be in the range of visible, and that average wavelength is 550 nanometer. Okay, so to get this kind of structure, so that means we can be able to get the 550 nanometer wavelength. So the assembly has been made. So assembly that consists of a plain glass plate and a plano convex lens. Okay, so the plain glass plate and plano convex lens, so what does it indicates? You can see how it has been placed. So the plain glass plate is placed at the bottom, and above that there is a plano convex lens. So once you place this plano convex lens on the plain glass plate, so these two, means the plain glass plate and the plano convex lens, they make contact at point O. Okay, so there is a point of contact, that is point O, and at the sideways you can see there is a gap which has been formed. Okay, so if nothing is there, so this gap which is filled up by the air medium, and therefore it is called as the air film, as we know. So this gap which is very minimum. Okay, so this gap is very minimum, and that satisfies the condition of your thin film. So therefore it is called as the air film. Okay, so once you got this kind of structure, that is assembly part, then you have to incident the beam of light on the top surface of the plano convex lens. So once the beam of light is incident on the top surface, so there is a partial action. So it get partly reflected to form a one ray, and then partly refracted, and through internal reflection it forms a ray 2. Okay, so there are the two rays which are been formed from the single ray. So ultimately our intention is to get the two coherent light waves or light rays. Okay, so we are getting the two light rays here, 1 and 2, that is generated from a single ray. So therefore we can say that these two rays are coherent rays. Okay, so this method we can call as a division of amplitude. So basically these rays, uh, these rays which are nothing but the waves. Okay, so the waves which are means incident on the surface of this plano convex lens, and half part of this particular wave that get divided, and it forms a reflected as well as the refracted, and then through internal reflection it forms another the ray, or you can say the wave also. Okay, so this is what the division of amplitude. So what is division? So you can see the statement that is mentioned here. So this involves the splitting a single light beam into the two beams. Okay, so splitting of single light beam into the two beam, and two beams are, one is a reflected beam and another is the transmitted beam. So these two beams we are getting from the single beam. So that method we can call as a division of amplitude. So this particular method, which is used in the expression of thin film, the uniform thin film. So what we did in the interference in uniform thin film, so we have considered a film whose thickness is T and having a refractive index that is say mu. So based upon this, we have derived the expression. Okay. So what we are considering here, there is a particular film of uniform thickness. So uniform means it starts from one end to the other end. So while solving the expression, we have considered the one end start from x, another is to y. So xy, that is the complete boundary, you can say. So up to this total the film area, so it maintains the constant thickness, that is T. So therefore it is called the uniform thin film. Okay. So above this film there is nothing, so there is a air, and below this film there is nothing, that is again a air. Okay. So air, which will be considered as your rarer medium, and the film area, which will be considered as a denser medium. Okay. So now next is we have to incident the broad source of monochromatic light on the surface of the film. Okay. So from this broad source there is a ray that will incident on this particular film area. Okay. So you can see there is a ray which incident on the film, and then once it will incident, so there is a partial action. So partial means it get partly reflected. Okay. So once it reflect, so there is a one ray 1 that has been formed. Okay. So you can see the ray 1 which is formed due to the reflection from denser medium to the rarer medium, because it reflect from the film area to the air medium. Okay. So the film which is considered as a denser medium, and the air which will be rarer medium. So if the reflection from denser to rarer medium, so there is a phase change, and that phase change correspond to the 180-degree. Okay. Or you can say the pi radian. Okay. If you talk in terms of radian, so it will be pi, and if it is in a degree, so it will be 180. So that 180-degree phase change, that correspond to the path difference of lambda by 2. Okay. So this is how we can be able to get the ray 1. Okay. So once again I repeat, so there is a beam which will incident obliquely on this top surface of the film area, and once it will incident, so it get partly reflected to form a ray 1. Okay. Next, now once it partly get refracted, so due to internal reflection, you can see there is an internal reflection, and through internal reflection because it happens only inside the film area. Okay. So there is no phase change at point this. Okay. You can see the downward point, so there is no phase change in this point. Okay. So the ray 2 that will come out with no phase change. Okay. So there is only a phase change that happens in a ray 1. It is because of the reflection from denser to rarer medium, but in ray 2 there is no phase change because it comes out directly through the internal surface. Okay. Or internal film area. So this is how we can be able to get the ray 1 and ray 2. Then after getting this ray 1 and ray 2, then we have solved the expression for the optical path difference. So in the expression we have seen how the geometrical path difference is correlated with your optical. So geometrical path means it is the physical measurement. So after physical measurement we have correlated with the optical, that is mu times the geometrical path difference. Then we got the equation 1, and then there is a simple substitutions. Okay. So after substituting we got the final equation, that is, I will just move directly to the equation. So you can see, so this is what the equation that we got for the total optical path difference, that is delta, which comes out to be 2 mu t cos r. We have mentioned by say plus minus of lambda by 2. Here only minus is mentioned. So it depends upon, some of the books they are only mentioned about the plus, some of the book they are mentioned about the minus. So no worry about this. So there, because we are considering that factor as either may be loss or it may be gain. If you say loss, so it may be minus lambda by 2. If you say gain, it will be plus. So therefore you can be able to take both the plus minus sign in the total optical path difference, that is 2 mu t cos r minus plus minus of lambda by 2. And then further it has been modified. You can see here mu is equals to 1 for air medium and cos r equals to 1 for normal incidence. So cos r is equal to 1 for normal. It means normal incidence means your beam of light which incident with the angle of 90 degree. So once the beam is incident with the angle of 90 degree, so there is a r which is means the angle of r that becomes totally zero. So if r becomes 0, so cos r value that become 1. So therefore, for normal incidence, directly you can say the cos r is 1. So that value is substituted in this. So you will get the optical part difference, that is twice t minus lambda by 2. And if you apply the condition of optical part difference, that is delta, which is m lambda, so you can be able to get the minimum thickness. Okay. So if your thickness that comes out with the lambda by 4, okay, so that can be the condition for the brightness. And if you will get the, in terms of lambda by 2, so that will be the condition for the darkness. Okay, so please try to remember lambda by 4 that is for the brightness, and lambda by 2 that will be for the darkness, that is destructive interference. So this is what the conditions that we have discussed about the plane parallel uniform thin film. Okay, so that was the uniform. Now next example that we have seen is the non-uniform. So how we can be able to get the non-uniform film? So that we have observed through the wedge-shaped air film. So what is wedge-shaped air film? So for that we have seen that there is a glass block which is placed at the bottom, and above this glass block there is a glass slide. Okay, so the glass slide which is separated by some spacer, and that spacer is your aluminum foil, because aluminum foil which satisfy the condition of your thick film. So thick film, because the thick film which has a particular range, it range between 10 micrometer to 50 micrometer, 10 to 50 micrometer. Okay, so if you have a range of particular film which is between 10 to 50 micrometer, so that will be considered as a thick film, and that thick film can be used as a spacer while studying the non-uniform film thickness. Okay, so here we have placed the glass slide above the glass block in such a way so that one side rests on the glass block and other side there is a aluminium foil. So once you place this, so there is a gap which has been formed between the glass slide and the glass block. So you can see in a modified diagram, you can magnify diagram. So here is the glass block and the glass slide, and there is a gap which has been formed. Okay, so this gap, as you know, there is nothing, so it means there is a air. Okay, so this gap which is filled up by the air medium, and as the shape of this film area, you can see here the shape of this film area is, it look to be like a wedge. Wedge means ramp. Okay, or slope. Okay, so you can see at one end where there is a point of contact, so at the point of contact that we can call as the apex point. So at the point of contact, the thickness of the film is almost zero. The thickness of the film is almost zero, and it progressively increasing toward the other end. Okay, so if you want to write the definition of say wedge, so what is wedge? So wedge means a particular film or wedge shaped air film or wedge shaped thin film. So what could be the definition? So definition will be, so a film whose thickness is minimum at one end, that is t is very less than lambda. Okay, when t means the thickness of the film is very less than lambda at one end, and it progressively increasing toward the other end. So that kind of structure called as wedge shaped film or wedge shaped thin film. Okay, and this particular gap which is filled up by the air medium, so therefore it is called as the air wedge or wedge shaped air film. Okay, so please try to make ensure about the definition of this wedge shaped air film. So once you got this kind of structure, so as we know, the thickness is continuously changing from one end to the other end, so that consider as your non-uniform film. Okay, so this is what we can be able to say the non-uniform film. So this is now the setup, the entire setup of this wedge shaped airframe. So what are the other parts of this entire setup that we can be able to see? So once the assembly part is clear, so any doubt in the assembly part first? Yes, any doubt if you have, please raise. what we are consider, how we have shifted from uniform to non-uniform. So please try to understand. So non-uniform means the thickness is continuously varying. In previous case we have seen the thickness that remained constant, so therefore that was the condition for uniform. Now here is non-uniform, the thickness is varying. Okay, then other parts of this setup is the sodium lamp. So sodium lamp basically has been considered as a source of monochromatic light. Okay, so source of monochromatic means it emits the beam of light with a yellow color. Okay, so the yellow color beam of light that will incident from this sodium lamp, and it will be in the broader manner. Okay, so the broad source of light will incident on the convex lens part. Okay, so there is a convex lens which is placed in front of the sodium lamp. So this broad source of light that will brought together on the convex lens, and the purpose of this convex lens is to convert that extended source of light into the parallel form. Okay, so once the light get converted into the parallel form, so this parallel beam of light will incident on the glass slide. Okay, so there is a glass slide, you can see here. So there is a glass slide which has been placed in such a way so that your reflected light that will fall exactly normal on the this assembly part. Okay, so it should fall normally on the assembly part. So how you can be able to fall the light normally? So for that, this light reflector or the glass slide which has to be kept at 45-degree angle. Okay, so you have to maintain the angle 45. So how you will ensure ki, means it is at 45-degree? So simple answer, ki you are observing the pattern through the microscope. Okay, so if you are able to get the clear visible pattern, so that is the simple indication that you have maintained this light reflector at the angle of 45-degree, and your reflected light that exactly falling normally on the assembly part. Okay, so that is the clear indication ki if we are getting the clear visible pattern, so the pattern look to be in this manner, that is fringe pattern is alternate dark and the bright fringes with the equidistant lines. Okay, straight equidistant line. So this kind of pattern that we will be able to see while studying this, or while taking the observation through the microscope. Okay, so this is what the arrangement of this waist shape air film. Okay, so once you have done the assembly part, then you have to incident the beam of light on the light reflector. So light reflector will complete the partial job, means it will reflect the light toward the assembly part, and it will transmit the light toward the microscope. As you can see, there are the two arrows that we have mentioned. One is the coming arrow, another is the going arrow. So one coming and going, it means the light which will incident on this, and after that it will get reflected. So if the light incident is exactly perpendicular, so there is no reflection which angle which will be formed, it will just come back. Okay, so therefore cos r that become 1 for normal incidence. Okay, so please try to understand this. Okay, so this is what the air wedge. And then there are some basic formula that we have discussed, ki how the pattern, or why the pattern look to be in this manner, ki why the first fringe that appears to be dark. So for to answer this, so we have some conditions. You can see the part difference, that is 2t plus lambda by 2. Okay, this equation that we have taken from the previous one, you can see here, this is 2t plus minus, or there is only minus that I mentioned, but it is plus minus of lambda by 2. Okay, so this condition that we have taken, so the part difference, that is 2t plus lambda by 2. So for constructive interference, that is 2t plus lambda by 2, which is equals to m lambda. So it will come out to be 2t, which is equals to m minus 1 lambda, m minus half lambda. Okay, or either you can be able to get the plus answer also, because if you consider say 2t minus lambda by 2, so you can be able to get the m plus 1 lambda, m plus 1 by 2 lambda. Okay, so these are the different conditions. Or if you complete this total, so your thickness that comes out with the lambda by 4 for constructive interference, and for destructive interference it will come with the thickness, that is t, which is equals to m lambda by 2. So that will be destructive. So it is a clear indication ki if your thickness that is of the order of lambda by 4, then and only we can say that it will satisfy the constructive, and if your thickness is of the order of lambda by 2, so it will be a destructive interference. Okay, and then this is important note, that is when m equal to 0 means if the order of the fringe is 0, so that is the point of contact, so it gives rise to a first dark fringe. So why the first dark fringe means the first fringe is appear to be dark is the clear answer. Key why it appears to be dark, because at the point of contact, so interfering waves, they interfere in a opposite manner, the phase difference they introduce. Okay, so therefore their intersection that produce a minimum amplitude that is almost zero, so the amplitude become zero at the point of contact. So if the amplitude becomes zero, so directly it is an indication that it satisfies the condition of destructive interference. Okay, so if condition of destructive interference is satisfied, then we can be able to say the apex point, that is the point of contact, that become dark. Okay, and your fringe pattern that will appear on the top surface of the glass slide. Okay, so you can be able to see this pattern with the naked eye. Okay, but in case of uniform film, we have seen the rays are parallel, so parallel rays never intersect, so that pattern we can call as a localized at infinity. But in this case, in non-uniform film, the pattern can be seen on the top surface of the glass slide. Okay, so we can be able to see the pattern with the naked eye, but only for the observation purpose we are using a microscope lens, so that means we can be able to get the clear visible pattern. Got it? Okay, so this is the important point, ki why the first fringe that appears to be dark. So it is the answer is the thickness of the film is very less than compared to the wavelength, that is lambda. Okay, so t is very less than lambda, and it satisfies the condition of destructive interference, so therefore it gives you the dark fringe. Okay, so first fringe that appears to be dark, and afterward it produces the alternate bright and the dark fringes. And now next is, now what is the distance between the consecutive bright and the dark? So for that there is a fringe spacing, so that will denoted by say d or maybe say beta, you can able to use. So d, which is equals to lambda upon 2 tan theta. So this is the expression that we got. So as there is no derivation part in your syllabus here, so only the theoretical concept as well as the experimentation. So therefore directly I have taken this expression, that is d, which is lambda upon 2 tan theta. So here the lambda, which is a wavelength of monochromatic light, and the tan theta, the theta which is called the wedge angle. Okay, the angle which has been formed between this conic area. Okay, so there is a theta which is a wedge angle. So this angle theta, which is very small as compared to means for the small angle, we can say the tan theta which is nearly equals to the theta. So theta that remain constant for a particular assembly, and your lambda is also constant. So your fringe spacing, that is d, which remain constant. Okay, so that is again an indication key the fringe pattern that appears to be a equidistant fringes. Okay, so why it appears to be equidistant? It is because of the beta constant. Okay, so these are the some important point that you have to remember. Ki the first fringe that appears to be dark, then these are the alternate equidistant fringes. So why equidistant? It is because the beta that remain constant, and these fringes are called as the localized fringes, because localized means these fringes can be seen with the help of naked eye. Okay, so we can be able to visualize these fringes. And then there are some other tricky questions like if the light is being used, so sorry, if the white light is used, then what kind of pattern we will get? So simple answer, if the means your monochromatic light is replaced by the white light, so if you replace that by white light, so you will get the alternate bright and the dark, but in case of monochromatic. But if you replace that with the help of white light, so that dark pattern that will remain same, but wherever there is a bright pattern, so that will convert into the color pattern. Okay, so it will be the colorful pattern, the color fringes will be observed if you replace by the white light. Okay, so this is what the answer. Then a third one is, if the angle theta is too great, then the fringes will be too close. As if you look at the formula, so it is d, which is equals to lambda upon 2 tan theta, So if you increase theta value, so naturally your beta or say d, the fringe spacing, that go on decreasing. Okay, so if there is means theta is too large, and in that case we will not be able to see the pattern. Okay, so that is the one reason we can be able to say. And if you think in other way, if there is no theta formation, so theta is totally zero, so in that case the both the slides, like this bottom one and the top one, they becomes exactly parallel, so there is no angle formation. So in that case we will not say that there is any kind of pattern that will appear. So there is a complete disappearance of the fringes. Okay, so fringes completely disappear when theta become 0 degree. Okay, and if you consider, say, when theta is very close to 1 degree, so interference patterns start vanishing. Okay, so please try to understand the words that I am using. When theta is very great, then there is a very close pattern, means you will not be able to differentiate the pattern. Okay, because it is alternate dark or bright, so it becomes very difficult to differentiate between the pattern if the theta is too large. Okay, it's a very close pattern. And if the theta becomes 0, so it is completely disappearance. And if the theta is very close to 1 degree, so the pattern start vanishing. Okay, slowly it vanishes, and if you reach to the theta equal to 0, so it completely disappear. Okay, so please try to understand these things. You have to know the what are the different methods that you can do to apply, so that means we can be able to answer the some tricky questions. Okay, so this is what about the fringes or the pattern due to the non-uniform thickness. Okay, then there is another example of non-uniform thickness, so that is the Newton's ring. So Newton, who has invented this concept to study the circular pattern, the fringe pattern that appears to be the circular ring with the central spot dark, and this is due to the reflected light. Okay, so now why such type of pattern that will appear, and what could be the setup? So you can see the setup is almost very much similar as your air wedge, only the assembly part has been changed. You can see in the assembly there is a glass block at the bottom, and above this glass block there is a plano convex lens. Okay, so the plano convex lens is placed because one side is a top side is a plane and the bottom one is a convex part, so therefore it is called the plano convex lens. Okay, and remaining parts are same. You can see the source of monochromatic light, that is sodium lamp, then there is a convex lens, the glass slide, that is a light reflector, and the microscope. So all remaining parts are same, only a change in the instead of simple glass slide, now here is a plano convex lens. Now this plano convex lens is been mounted on this glass block. So after mounting, so this plano convex lens, it make a contact at some point, that is the center point, you can say, and at the side way there is a gap which has been formed. Again, this gap which is filled up by the air medium, because nothing is there, it means it is filled up by the air. So that become your air wedge between the lens and the glass block. Okay, so the gap which is filled up by the air, and it satisfies the condition of thin film, so therefore it is called as the air film or air wedge, because again wedge means it has a minimum thickness at the point of contact and it progressively increases toward the other end. Now the difference between the previous case and here is the curve part, and in previous case it was a straight part. Okay, here is a curve on both sides. On both sides you can see there is a curve, and at the center it is a point of contact. So as simple answer key why the pattern appears to be in this manner, the center spot dark. So simple answer, you can see these rays are nothing but the waves. So one wave which has been coming and it will incident on the center part, and then again it get reflected back. So their intersection that produces the point of minimum amplitude. So at the point of contact, the thickness is 0 as well as amplitude is also 0. So if amplitude becomes 0 at the point of contact, so it satisfies the condition of destructive interference. So therefore your central spot that appears to be dark. Okay, so it is a broader one because the point of contact is a larger area. So therefore it is a broader spot. Okay, the broader dark spot that will appear at the center is the why Again I repeat, so it satisfies the condition of destructive interference. Okay, then now why it is in a circular manner? So circular manner, as you can see, so every time your locus means the one particular ring which will be generated from one point, then another from the another thickness point, then next likewise, okay, and so on. So every time your center point that becomes fixed, that is called as the locus. Okay, so if the locus is fixed, as we have seen in previous chapter also, if the locus, that is the center point, which is fixed, so naturally it will trace a circle only, so therefore it appears to be a circular pattern. Okay, so that your locus, that is fixed point, is at the center, so therefore every time it will try to trace a circular pattern, so therefore you are getting a circular ring. So and these rings and this entire experimentation which is done by the Newton, so therefore it is called as the Newton's ring or Newton's ring experiment. Okay, so this is one of the example of your non-uniform thickness. Okay, now there is some conditions that we have to understand ki how the non-uniform thickness can be used to get the two reflecting rays. You can see here. So here one part that we have mentioned here. So this is a curved part of the plano convex lens, and there is a plain glass block. Okay, so in between there is a air medium, and now you can see the light wave that will incident at point A, and through this you can see here there is a ray 1 which has been formed and the ray 2. So ray 1 which is formed as ray 1 no phase change, and the ray 2 reflected with the phase change of pi. You can see here clearly it is mentioned. So ray 1 which is reflected through the same medium, that is the convex lens. Okay, but ray 2 which reflect from the glass block to the air medium. Okay, it reflect from glass block to the air medium, so therefore at point B you can see there is a phase change of pi radian. Okay, so what is the path difference between the ray 1 and ray 2? So we need to calculate, and then based upon this path difference, then we can be able to get the condition of constructive and the destructive. So again the condition will remain same. So for constructive, the thickness, the minimum thickness, that should be of the order of lambda by 4. Okay, and for destructive it should be of the order of lambda by 2. Then and only we can be able to get the bright as well as the dark pattern. Okay, then there is an expression for radii of the dark ring. So this is what the diagram that we have mentioned here. So that means we can be able to get the radius of this plano convex lens. Okay, so this is your experimentation part, means while performing the experiment, either you can be able to find out the wavelength of monochromatic light. If the wavelength is given, like suppose it is given say 5893 Armstrong unit, so what could be the radius of this plano convex lens? So that you can be able to find out with the help of experiment. Okay, so for this you can see the plano convex lens and the dotted line that indicate the complete radius of this plano convex lens. Okay, so capital R that indicate the radius of the plano convex lens. So simple geometry has been applied here. So this part is your thickness of this plano convex lens, and this is your R, the small r, that is you can see here. And through this we have considered this particular triangle, and then simple the theorem which has been applied. So it is r minus t square plus r square, which is equals to capital R square. So therefore r square, if you solve this bracket, so you will get r square which is 2rt. So if for large r, the small t, because you have to remove, if you compare this capital R with the t, so it is 2rt, which is very greater than the t square. So therefore t square can be neglected, and you can be able to get the radii of the dark ring. Okay, so for radii of dark ring, that is r square, which is comes out to be m r lambda. Okay, so this entire expression we will do in the next lecture. Just glimpses of this, how we can be able to get. So that means a stepwise manner we will complete that expression part also. Okay, then some of the important points related to this Newton's ring. So by d, which is equals to lambda upon 2 tan theta, as the thickness of the airframe increases gradually outwards non uniformly, the separation between the fringes decreases. As you can see what the statement is mentioned here. So by d equals to lambda upon 2 tan theta, so d is your fringe spacing, and lambda is the monochromatic wavelength, and tan theta. So here the theta that doesn't remain constant. So theta is changing progressively. Okay. In previous, if you think about a wedge-shaped airframe, so in that case, the theta remain constant. So therefore, it appears to be the equidistant fringes. Okay. But here the theta is progressively changing. You can see the diagram. So it is a arc, the curve structure. So whenever you have to find out the theta, you have to draw the tangent, and then you can consider a particular triangle, and then you can say this is a theta. So the theta is progressively changing. So therefore your pattern that appears to be in this manner. You can see it is not the equidistant fringes. Okay. So if you are moving toward the center, the distance is large, and if you are away from the center, the distance is narrow. So why it happens? It is because as the order of fringes increases, order means zero position is at the center, and then your m value or n value that progressively increases. So theta is not increased in the same proportion. Okay. So both are not increased, means your order, if it order is say 1, so theta is not exactly 1. So both the proportions are not in a same manner. Okay. So therefore the pattern appears to be means it is not the equidistant, you can say. Okay. So therefore, means if you are toward the center, the distance is large, and if you are away from the center, the distance is narrow and narrow. Okay. So it means it becomes a closed pattern if you are away from the center. So this is what the pattern appears to be in case of say Newton's ring experiment. Okay. So in Newton's ring, the things that you have to remember, one is why the center spot dark. So the center spot dark, it is because this is the point of contact. So at the point of contact, the thickness of the film is minimum, that is almost zero, or you can say T is very, very less than lambda, and it satisfies the condition of destructive interference as the amplitude becomes zero. So therefore, the center spot appears to be dark due to reflected light. Okay. And then why the pattern is not equidistant? So simple answer, key as the order of fringes increases, so your theta doesn't increase in the same proportion. So therefore, if we are toward the center, the distance is large, and if we are away from the center, the distance get narrow and narrow. Okay. This is the second point. Then third is these fringes that we can be able to see with the naked eye on the top surface of the plano-convex lens. Okay. So this entire pattern we can be able to see or observe with the help of naked eye. So therefore it is called as the fringes localized. Okay. So fringes are localized, means it can be seen with the help of naked eye. Got it? So these are the main important points of Newton's ring, and why it is in a circular manner. So that is the fourth point. So why it is circular? Okay. So ultimately, while experimenting, you have to find out the diameters, and then you can be able to go for the radius of the plano-convex lens. So this is what the Newton's ring. Okay. So now the derivation part that we will do later on, maybe that derivation part is been skipped in your syllabus, but still how we will be able to get the condition, so at least we can be able to see. Okay. As once again I repeat, the course material of this unit that also I have been shared on your Google Classroom. So please go through it, and if you have any sort of a query, please raise that query also and start your preparations. Okay. Because maybe within 1 or 2 lectures we are going to complete this unit also. Okay. So then afterwards we will revise both the units, unit 1 as well as unit 2, for your CA examination. Okay. So any doubt? Okay. Okay, if there are no doubts, so hopefully we can be able to complete, but maybe other 2 lectures we require to complete the theoretical, and one more lecture we will go for the numerical. So at least 3 lectures. So within 3 lectures we can be able to complete this unit also. Okay.
Yes.
Okay. So thank you.
Thank you, sir.
Okay. So I'm closing the meeting now. Okay.